Okay, we are looking at part A of number 4 on page 99 of the workbook. This is a little bit more practice with determining whether or not a series converges using the full range of tests that we have so far. Okay, you may be getting better at sort of telling which tests are going to work and which aren't. I'm going to continue to use the step-by-step process here and look at this series and maybe start by asking, might the test for divergence work for us here? Let's give it a try and just see. Okay, well, using that test again amounts to taking the limit as n goes to infinity of the nth term. Okay, we wind up with a limit of the form infinity over infinity, so we can use L'Hopital's rule on that. And the derivative of e to the 2n plus 1 by the chain rule is going to be 2e to the 2n plus 1. And notice that the top of that fraction is constant, the bottom goes to infinity, so we're going to get 0, which is unfortunately inconclusive. This test does not help us. Okay, you may have been able to notice that that was going to happen just by looking at the function itself. 3n and e to the 2n plus 1, e to the 2n plus 1 grows a lot faster than 3n does. Okay, so it's kind of not surprising that we're going to get a 0 out of that. All right, so what's next on our list of convergence tests? Well, ratio test might be something that we could try. Okay, and there's some evidence that that might work for us because of the e raised to the 2n plus 1. E is a constant raised to a variable power. That's one of the things that indicates to us that the ratio test might work well. All right, let's do it and see what happens. Okay, so the way the ratio test works again is to take the an, okay, that's the term in our series, and to start by taking the limit of the absolute value of an plus 1. That means we're going to replace every n with an n plus 1. And then we need to divide by a to the n, which is like multiplying by the reciprocal of a to the n. Okay, so if we flip the a to the n, it looks like this. Okay, now here the algebra gets a little bit more interesting than in some of the problems we've done so far. So we maybe take the 3 and multiply it through to get a 3n plus 3 as our first step. Okay, so we're just distributing the 3 through. We've got an e to the 2n plus 1 up here. And then down in the bottom, we've got an e raised to kind of a long and ugly power, 2 times n plus 1 plus 1. Okay, if you distribute that all out, 2 times n plus 1 is 2n plus 2 plus an extra 1. So that's going to be e to the 2n plus 3 after we do all that algebra. And that's going to be multiplied by 3n. Okay. So the question is, what can we cancel here? All right, well, the thing that kind of comes to mind for me is the two things that have e's. Those are constant bases, so we should be able to cancel. And the question is, what survives after we cancel? Okay, well, we've got a 2n plus 1 in our power on the top and a 2n plus 3 in the bottom. Notice that the number 2n plus 3 is exactly 2 bigger than 2n plus 1. So what that tells us, really, is that there are 2 extra factors of e in the bottom. Okay, after we cancel, we're going to get an e squared down there. Okay, and so if we rewrite this, I'm going to take that e squared, that's a constant, and just pull it outside of the limit sign. Okay, we can pull constants out of limits the same way that we can pull constants out of integrals. And what we're left over with is just the limit as n goes to infinity of 3n plus 3 over 3n. Okay, and that's a limit that we can do using L'Hopital's rule. So we've got the 1 over e squared, that's still there. And then if we take the L'Hopital's rule and apply it to that limit, we're going to get a derivative of 3 and 3 on the top and the bottom. So that 3 over 3 just becomes 1. And what we wind up with here is just 1 over e squared. There's our value of r. Okay, and again, the way that the ratio test works is that if we get the value of r and it ends up being less than 1, we know that we've got a convergent series. And so here comes our proof. So since r is 1 over e squared, that's a number that's less than 1, we know that the given series must converge. Okay, and there's our answer.